Okay, sorry about that. My video got cut off, so I have to record it in two halves. I hit the wrong button. Okay, one second. Just bear with me here. Where is the? This thing just ticks me off. There it is. Okay, F5 swap. Minimize that. Okay, comments. Let's talk really quickly about comets. I don't got a lot of time to my next class. Normally, we look out into outer space, comets. Like, one of the misconceptions about comets is you can see them zipping across the night sky like a shooting star. And that is false. When you look at a comet in the night sky, you really can't see it moving. It's so far away from us, right? It looks like you don't see stars moving in the night sky except with the rotation of the Earth, and as things move across the sky, they move slowly, right? Just like the moon moves slowly across the sky. Comets, because they're so far away, we can't see them, moving. Right? If they were really, really close to us, we could see them just like a shooting stars in our atmosphere. It would zip right through our sky super fast. Because it's so far away, it doesn't look like it's moving at all. You have to sit there and take a picture at say 11 p.m. and then take another picture at 10 minutes later and compare the distance, right? How far it's moved because they are so far away. So in the night sky, what you would see is this fuzzy patch of light normally. That would be the comet. We can't make out all these details with the naked eye. Right, so comets are usually seen as faint, fuzzy patches of light traveling in highly elliptical orbits from the Oort cloud. Okay, some of them can come from the Kuiper belt, though. Right? So the structure of a comet, we've got the nucleus. The nucleus is a frozen ball, and in that frozen ball, we've got frozen gas and dust. Right, so we got like methane, ammonia, carbon dioxide, water, but all of these things are frozen into ice. And they can be quite large, a few kilometers across. Right? That's pretty big. If one of those hit the planet, it would do a massive amount of damage. Now, as this nucleus gets closer to the sun, it starts to heat up. It goes from ice cold, right? Beyond ice cold. Ice cold is 0 degrees Celsius. It goes from like negative 270 degrees Celsius, gets close to the sun, and it starts to heat up really quick. Right? So when the nucleus starts to heat up, these frozen gases, right, they sublimate. They don't become liquid. They go right from being a frozen solid to becoming a gas. That's sublimation. They kind of skip the liquid phase. And when they do that, these gases, right, they start getting vented out of the comet, and they create a fuzzy haze around the nucleus. Right, this is known as the coma. Right, so when a comet approaches the sun, the nucleus warms and the frozen gases sublimate. Sublimate means going from a frozen solid to a gas, right? Skipping the liquid phase. So they sublimate into the gaseous state and expands outward into space. The coma gets larger and brighter the closer the comet gets to the sun as it gets hotter and hotter. Right? So that tail of gas that trails behind the comet can be up to like 100,000 kilometers. Right? It can be they can be quite large. I shouldn't have said diameter there. That's wrong. It's not diameter. Right? So we got the comet here, And often in the comet, we see two tails, right? First of all, the coma is that haze of gas, right, behind it, giving it a fuzzy appearance, right? And then we've got a tail of all the dust that was trapped in the ice, right? And I'm saying ice to include water, methane, ammonia, all the other frozen gases, right? So we get all the dust coming off of them, right, creating a dust tail, right? And then we also get the ion tail, right, which is made up of plasma, energized particles. So the dust tail is the unfrozen material that's getting blown or kind of flowing off the comet. The ion tail is caused by the solar wind, right? Those energized particles coming off of the sun, that solar wind interacts with the compounds that make up the comet, right? And those gases get excited by the energy in the solar wind, and they form a plasma, right? Matter that has its electrons being stripped, right? A really simple way to think of plasma, like think of um, well, very simply, not quite accurate, but will help us understand. Think of the material inside a neon light. When electricity runs through it, it gets excited and it gives off light. Something similar to that. So comets generally have two tails, right? With the naked eye, you normally only make out one tail, the dust tail. You normally can't see the ion tail unless you have some optical equipment helping you. So the ion tails, made up of ionized molecules and generally flow in the direction of the solar wind. They'll flow directly away from the sun. Okay? The dust tails are usually broad, diffuse, and gently curved as they follow the orbit. So if this is the sun and we have a comet flowing around the sun in this direction, okay, it's going this way. Okay, as it gets closer, the dust tail gets bigger, but the dust tail is being affected by the solar wind. The solar wind is blowing on the dust, but that dust tail is generally trailing along behind the comet. Okay, so it trails along behind the comet, following along its pathway. The ion tail is always pointing directly away from the sun. The solar wind creates the ion tail, and the solar wind blows the dust tail a little bit behind the comet. Right? So normally you expect it to follow exactly 100% behind the comet, but the solar wind can push on the dust tail a little bit too. This image here is showing Halley's Comet. It's a short period comet. It returns every 76 years. Right? And you can see as Halley's Comet got closer and closer to the sun, you can see that its tail was always kind of pointing away from the sun. But as it got closer and closer to the sun, the tail gets larger and larger. And as the comet starts moving away, right, its tails again being its tails are being blown away from the sun. But as it gets further and further away from the sun, it gets less and less bright. Its tails get smaller and smaller because the comet is cooling. There's less melted material. There's less freed gas. Okay, the orbit of comets. Comets, they travel in a large elliptical orbit, perihelion, right? Helion from Helios, the name of the Greek name of the sun, right? Perihelion is when they're closest to the sun. Aphelion is when they're furthest away from the sun. So many comets break up as they come close to the sun, right? Perihelion. Many others continue their journey and they'll spin around the sun and they'll go back out into the solar system. Short period comets, they have an orbit of less than 200 years. They originate within the Kuiper belt, right? And the gravitational interactions with the outer planets can pull it out of their orbit and out of the belt and send it into an elliptical orbit around the sun. Okay? And most of the short period comets, they're on the ecliptic. They're traveling along the same plane as everything else in the solar system, right? The Kuiper belt is is in the same plane as all the other planets because they're made out of the same protostellar disk, if you go back a few lectures. Long period comets, though, greater than 2,000 years, so it takes them more than 200 years to complete their orbit. Many of them take thousands or hundreds of thousands of years, right? Because they're coming from the Oort cloud, and the Oort cloud is so far away, right, that these distances are enormous. And they don't always go along the ecliptic. Here, this comet is traveling, almost perpendicular to the ecliptic. So long period comets, their orbits take hundreds of thousands of years, right? The majority are in that group. Only a few of their orbits bring them within the inner solar system, so bring them close enough to like Earth that we can see them. Many of them, there's many comets that are coming back into the solar system, but they'll never pass close enough for us to see. And the Oort cloud comets, their orbits are not confined to the ecliptic. Okay, this image here is showing the nucleus of a comet. Sorry, I just need to pause it. I gotta wipe my nose. So this image here is right here is showing the nucleus of a comet, right? And they're actually quite dark. You can see that the surface is quite dark, but you can see these bright spots where, we've got like a rocky outer layer, and inside there's the frozen ice and, methane, ammonia, water. And you can see that they're melting and these gas jets are showing up, which create the fuzzy coma, which then creates the dust tail and the ion tail. Okay, leaving comets behind, we're going to talk about what characterizes a planet. Pluto used to be considered a planet. Okay? But in the Kuiper Belt, we found other objects in the Kuiper Belt that are even bigger than Pluto, right? Some as close to Pluto, but some bigger. For example, Eris here, that's bigger than Pluto, right? We thought Pluto was a planet, but there's other objects in the Kuiper Belt, right, that are bigger, right? So here's the sun, here's Neptune, right? Pluto's orbit into the Kuiper Belt. Eris, here's its orbit. Okay? So Neptune is the last planet. Pluto we don't consider a planet anymore. Okay? We consider it a dwarf planet or a planetoid because it doesn't fit all the criteria to be a planet. So once an object larger than Pluto was discovered and a new understanding of the outer solar system arose to include large trans-Neptunian objects, we had to create a new definition. So we started discovering objects past Neptune, right, that were larger than Pluto, and there were several of them, right? Eris had its own moon. Right here we got Pluto with its moons, Makemake, Haumea, Sedna, right? All these other ones, we see these large objects, right? We don't call them planets, right? We call them planetoids or dwarf planets. So for a body to be considered a planet, it has to meet these three categories. It has to orbit the sun. It must be big enough that its own gravity pulled all its material into a sphere. And the third, it has to have cleared its neighborhood around its orbit of other bodies. Okay? So what we mean by that is it has to be the largest object in its orbit. Okay? Pluto's orbit, if we go back here, Pluto's orbit, right here, it crosses the orbit of Neptune. Okay, so if we were to look at these two objects in their orbit, at this point where their orbits overlap, Neptune is the largest. Pluto is not the largest at this point. So Pluto lost its status as a planet because it hasn't cleared its neighborhood. right? It's not the largest object in its orbit. Okay? It is not the biggest object. So because it didn't classify the third condition, it's considered a dwarf planet. And dwarf planets that exist beyond Neptune, we call them Plutoids. Okay, the last topic here for the solar system, the idea of the heliopause. So I want you to imagine the solar wind traveling out from the sun. Okay? And the solar wind eventually starts losing strength. Right? And all the stars around us, they're all emitting radiation as well. Okay? So the solar wind is pushing against that radiation coming in, but eventually the solar wind loses strength. Where the solar wind tapers off and stops having strength is where we cause the heliopause. So the heliopause is a theoretical boundary where the sun's solar wind is stopped by the interstellar medium, where the sun's solar wind is no longer great enough to push back the stellar winds, right? The particles coming off of surrounding stars. This is the boundary where the interstellar medium and the solar wind, where their pressure balances. And this heliopause, our solar wind, deflects the cosmic radiation from other stars and possibly protecting us from deadly radiation from the cosmos. Okay? So, actually, don't even really worry too much about all the details of this image. It's kind of like an artistic rendition. But here would be the sun, right? And then this represents how far our solar wind can travel. And here is representing cosmic radiation outside of our solar system pushing against the heliopause, right? The heliopause, again, our solar wind pushing out, deflecting incoming radiation from around our star, right? So radiation from other nearby stars, and where those two pressures are equal, right? We have the heliopause. And the heliopause is thought, right? We don't have, it's again, this is theoretical, but the heliopause is thought to deflect cosmic radiation and protect our solar system from, radiations outside of our sun. Okay.